Now we consider asymmetric encryption methods in our OpenHPI course, Confidential Communication in the Internet. You remember the characteristic of this asymmetric encryption methods was that they use two keys. They use a key pair for encryption and for decryption. So the private key, this was one of these two, must be kept secret. Only the owner of the key pair can know the private key. No one else, no communication partner is allowed to know him. And then we have a public key, and the name public comes from the fact that this key have to be made available to all the other communication partners. Now the idea is we can take a message and can encrypt the message with a public key, and then the only way to decrypt this document is to use the corresponding private key. And the same is true in the reverse direction. A message can be encrypted with a private key, and then it can only be decrypted with the corresponding public key. An important objective is that it is practical, as least practical, impossible to construct the private key from the public one. The public one knows everyone, and so it should not be possible for anyone to conclude from the public card from the public key to the private key. So what are the prerequisites for such an asymmetric encryption? Each participant in this communication have a key pair, have a private key which they have to hold, which have to keep secret, and a public key which is public accessible. The private key can be securely assigned to a participant because only this participant has this private key. No one else knows it. So now let's look how the encryption is working. The encryption is working. Let's take a message, and then the message should be sent from Bob to Alice. Then Bob, who encrypts the message, takes a public key from Alice, encrypts the message, and sends it to Alice. And then Alice is able to decrypt this message by their own private key. So we have the text, we take the public key from Alice, we encrypt this with our function, and then with a private key of make Alice. Moment, I have to. This was a public key of Alice, and Alice is then able with a private key to reproduce the original text out of this encrypted message. So, and the encrypted message stays confidential. After Bob has encrypted the text, this is the ciphertext, has encrypted the text with the public key from Alice, no one else, only Alice is able to decrypt the text because she has the corresponding private key. So encryption of a message with the subscriber's private key allows anyone to verify the message really originates from the sender. So if we encrypt the message with the private key of Bob, then everyone knows the public key of Bob. Everyone can take the public key and can decrypt this message, and in this way he or she can conclude this message comes definitely from Bob because he was the only who was able to encrypt it in such a way with his private key that it could be decrypted with his public key. Here Bob takes the private key of a text. This is encrypted, this is a ciphertext, and anyone who applies the decryption function with a public key of Bob gets back the text. So here, with this application, in this form of application, we can ensure the legal binding of the message and its sender. And in this way, we can prove the authenticity of the sender. But both approaches only work if the public key is not compromised. It's really clear that this is the public key of Alice, or the public key of Bob. And second, that the private key was kept secret. So these are the basic idea of asymmetric encryption. And now let's have a closer look to the most famous, most popular encryption algorithms, asymmetric encryption algorithms, the RSA algorithm. So RSA encryption is the most famous and most widespread asymmetric two-key encryption. It was, and the name comes from the developer. It was developed in 1977. Ron Rivest is a famous such algorithm designer for such cryptographic algorithms. Adi Shamir is a famous security analyst who analyzes and such crypto analyst. And Leonard Edelman was a PhD student. And they developed in 1977 this RSA algorithm. And in complete difference to the symmetric encryption algorithm, the asymmetric encryption algorithm like RSA are based on difficult mathematical problems. And in case of RSA, it is a mathematical problem of factorization. That means the check whether two very large randomly selected prime numbers, whether a big number, which is a product of two very large randomly selected prime numbers, can be factorized without the knowledge of these two prime numbers. This is a factorization problem. And when we speak about large numbers, then it's numbers with more than 100 digits. So the RSA procedure, and we show this how it works at hand of small numbers. In practice, of course, these are huge numbers which are used here. The starting point is that one has to select two prime numbers. We take some small one, we take 17 and 31, and then calculate the product, the n. The n, p times q, and in our case, n 17 times 31 is 527. So the attacker has to answer the question, has to find p and q out of this number, and this is almost impossible if p and q are very large prime numbers. Then the third step is that the so-called Eulerian phi function is computed. And this is in case of the product of two, if n is a product of two prime numbers, it's quite easy, because it's simple, the product of p minus 1 times q minus 1. And in our case, the Eulerian phi function can simply be computed 17 minus 1 times 31 minus 1, and this is 48. And then we can generate the key pair for the two participations in our communication. So to this end, we select number e, which is smaller than the Eulerian phi of n function, and it is not divisible by this. So for example, we can choose e equal to 13. It is smaller than 428, and it is not divisible. And then the pair 13 and our product 527, it's the public key. And then we have to find the multiplicative inverse D from E with regard modulo phi von n, and then this D gives the, in our case, computation it is 37 in our simple example, because E times D, 13 times 37 is modulo 48 is equal to 1. So this is a public key, and this is the private key of the participant of our communication. So in the end, only EDN are needed to generate the public key E von n, E point n and D point n. So now we can apply the procedure. So you have a communication partner who has his key pair, the public and the private key. We take the message. The message in this case is considered a number, and we compute the code, the cyber code, the cybertext of this message by computing this number to E modulo n. And the message can be then recomputed, decrypted from the cyber by cyber hoch D mod n. So, by the way, here we should better write cyber instead of code to see this number text. So the encryption and decryption with a private and public key now works as following. We have the message HOE gives the cyber code, and then we can, as a cyber, and then we can do this encryption and decryption in the reverse order, taking the private key for computing the cybertext and taking the public key for computing the message. You remember we had these two applications that we can encrypt with the public key, and then we can encode with a private key. We have this in both cases. So in our example, let's make it concrete now. The communication partner B, Bob, will send to Alice the message 456. It's also a very simple message, and it's a number because we have to compute number computation, but a string every time can be interpreted as a number. So B gets the public key EN, as we have described from A. So B takes, so this what we have ENN and DNN are the private and the public key from Alice. Bob will send Alice a message, and so he takes the public key from A and encrypts 456, the message 456 by 456 to the n mod n is 456 to 13 modulo, and it is this number. This is the cyber text of this message, and it's encoded with the public key of Alice. And then B sends the cyber text via the open internet to A, and then Alice can detect this by applying her private key. They can decrypt the cyber back to the original message simply by computing 447 to 37. This was her private key. Modulo is this way, and this is exactly our message 456. This is the encryption way. And the way around that Bob takes his private key to encrypt the message, this is a way to convince all the other communication partner that he, Bob, was the one who sent this message. A few remarks that this mathematical computation is really correct. And this is based on a mathematical theorem, the so-called Fermat's little theorem. We are here in the area of number theory. So this fact, this Fermat's little theorem says for any a and any prime number p, it holds a to the p minus 1 is congruent 1 modulo p, if and only if if a is not a multiple of p. So the chain of evidence now, if E times D equals 1, this was exactly how we computed the private key D from the selected E. Then there exists an X with the property that E times D minus 1 is X times P minus 1 times P minus 1. So this is a little bit complicated. It's not necessary to understand this in full extent. The people who are interested are invited to look to the more deeper information in other courses about internet security. But it gives a good feeling about the nature, how these asymmetric encryption methods are working, or they are computed. And now we have to look into more detail how they are implied.